we'd like to locate points where the second derivative is 0 and decide if they are inflection points. And this is my first of two problems that involve the derivative of natural log. Well, this function is not too terribly hard to differentiate. We take the first derivative and we get, it's the first term is a power rule. And then we have plus 1 over t. So this is our first derivative. The second derivative, well, this becomes a positive t to the minus 3, and then this is a minus 1 power, so we get minus t to the minus 2, just like this. Now, if you want to set this to 0, there's a few things you could do. I might write it like this. Oops, 1 over t squared. So here's the second derivative. And then we could get a single fraction as follows. So if I'm going to do one more step in simplifying. Okay, we can have a 1 minus t all over t cubed. Okay, so now it's pretty easy to set to 0. You know, we've discussed this, that a rational function is 0 only when the numerator is, and so we get one place, t equals 1. And we know, it's undefined where the denominator is 0, but this is not in our domain anyways. You can't evaluate this term at 0. Similarly, you cannot evaluate this term at 0. To determine if t equals 1 is an inflection point, we need to make sure that the sign of the second derivative switches so that it either goes from concave up to concave down or from concave down to concave up. And so you put 1, and then we want to test the second derivative. Well, here, the denominator, well, let's pick some positive numbers so that the denominator will always be positive. In fact, we really need to, because this function is not defined as 0 and it's not defined for negative numbers. So if we tested, for instance, a half, you can see that the second derivative at 1/2, well, this is 1 minus a half, which is positive, over a half cubed, which is positive. So you can see this is positive. And if we were to test, for instance, 2, 1 minus 2, okay, is negative. This one I'll write out. So this is negative. In fact, you can see the concavity switches. It goes from concave up to concave down, and so we do have an inflection point at t equals 1. But we want to show that this function d of t, it decreases for a while after t equals 0, and then it's always increasing, and then find the unique critical point. Okay, so whenever we're doing increasing and decreasing, we know it involves the first derivative. So we would like to take the derivative to look for critical points. So this is first times derivative of the second plus second times derivative of the first. So far, what I have differentiated is just this term. The derivative is here. And then I differentiate t. And then differentiating the 1, we have 0. So if I need to set this to 0, which I do, I might slightly clean it up. This is 1, then I have ln t, so I get ln t plus 2. So this is my derivative. Okay, so, this derivative in terms of critical points being does not exist, or where the derivative is 0, this derivative exists everywhere that's in the domain, and so we don't need to worry about does not exist. So I need to set it equal to 0 to look for critical points. And then I get ln t is -2. We know because of inverse functions, we could raise both sides to e to the This would give us t, and this would give us e to the minus 2. And so this is our one critical point. So in a way, this part, find the unique critical point we have. Okay, this is the one critical point. But now for the part to show it is decreasing and then increasing, we need to, and I need to evaluate the first derivative and see where is it positive, where is it negative. Okay, well, you know what I can do here? So this is where it's 0. I need something over here, but this must be a positive number or else it's not in the domain. I need something over here. We can choose on this side to be e to the minus 3, and on this side to be e to the minus 1. I'm doing that because, you know, I know that e to the x is an increasing function, and so this will be less than this number, and this will be greater than this number. But also, it's going to be very simple to look at the derivative. So if I take, this is just ln of e to the minus 3, we get negative. And then d prime of e to the minus 1. This is, you know, ln of minus 1, or ln of e to the minus 1, which is negative 1. And then this is positive. So I put minus and plus, and this means, you know, that this function is, to sort of finish our statement, this is increasing from e to the minus 2 to infinity, and it's decreasing from, well, 0 to e to the minus 2. Okay, and that's exactly what we were supposed to show.